Hi, and welcome to this video on oscilloscopes. This time around we're going to be talking about the functionality of oscilloscopes and what you can do with them, what the controls do, basically how they work. The one you're looking at right now is, well, it's an older version. It's what the class is a CRT type, which is Cathode Ray Tube. So it actually has a tube inside, which is the green display that you're looking at right there. And nowadays it's all done digitally. You tend not to see the old CRT type like this is. This scope's probably about 20 years old, and but still working well, and it still has a place in the lab on the bench. And as you can see at the moment, I'm producing speech patterns as I speak, and that's because I've got a microphone plugged into the oscilloscope, and that allows you to see my speech patterns. If I try and hold a note, you should see some waveforms. And that shows quite a complex voice pattern. So I'll just show you what I'm doing here. Okay, I'll stop speaking into the microphone now. So we've just got a microphone plugged in into here, and there's a cable comes through here, and then we've got that going through a couple of probes, well, a couple of connections rather, and that's coming around to the input of the actual scope, just there. So it's coming in here. Here's a quick rundown of the controls of the scope. I'm not going to go into every single control and knob, but the main important ones. First of all, you've got an intensity here. This is just for brightness, so you can turn the trace down, turn the trace up, just set it to a comfortable position. You don't want it too bright because you can damage the screen on these CRT type old version oscilloscopes. If you've got a modern one, you don't really have a brightness control. It's all done on an LCD panel or on a PC computer. You have a focus control, pretty much does what it says on the tin. You adjust that to get as sharp as possible display. You've got really the main controls here are those and the input attenuator. When the signal actually comes in through the BNC socket here, you can adjust the sensitivity of the signal. If you like, you can either look at it in terms of volts or millivolts. And if you have the control set like it is right now, it's set to the 10 millivolt position. And what that means is, for every 1 centimeter or graticule position on the screen, it takes 10 millivolts to move the line either positive or negative. So that's your Y deflection, if you want. You have Y, which is, if you like, up and down, or amplitude. And you have X, which is being shown right now. And if I slow the time base down, you'll see it as a moving dot. That's the time base moving the X deflection as a function of time. So it takes a certain amount of time to cross the screen. It's actually 0.2 of a second. That's 200 milliseconds per graticule, per 1 centimeter square. So it takes 200 milliseconds to get across each one of those 1 squares when it's set in this position. But the Y, as I was saying earlier, is for the sensitivity of the scope, and at the moment it's taking 10 millivolts, which is what we were showing with the microphone earlier, to move it in 1 centimeter. And you can adjust it. If I turn it up to here, this is now 1 volt per division per centimeter graticule position. So it takes a volt to move that dot up a box or down a box. That's 2 volts. That's 5 volts. So now it takes 5 volts to move the dot positive or negative. And I can show that if I just use a regular 9-volt battery. So just a standard square 9-volt battery. And if we connect this 9-volt battery to the input of the scope, we should see about almost 2 divisions of deflection, because that's a 9-volt battery, and it's going to take 5 volts to move it 1 square. So this is nearly 10 volts almost. So we're looking at not quite below 2 squares. So let's give that a go. I'll just put a DC voltage on here, just with a simple battery. So that's with the power on, with the voltage on. And as you can see, it's exactly right. It's just below the, it's not quite 10 volts. And that's with the that get off. So that's 0. I can probably position that a little bit better. There you go. So that's 0, and that's up there. So that's almost 10 volts, showing us that. And you can use the scope as a voltmeter at that point if you wanted to. Okay. And every time that goes on and off, you can see it's affecting the screen by the dot deflection by almost 10 volts. Of course, it's a 9-volt battery. Okay, so what's actually happening in the in the tube, in the actual CRT and the oscilloscope. Like I say, this is all a little bit out of date now, because nowadays everything's digital, but it's worth knowing how it works anyway, and you may well actually end up using a CRT type oscilloscope on your bench, mainly because they're very cheap now. You can pick them up second hand, really cheap, and they're still very useful pieces of equipment. So basically, inside what you have is a tube like that. Imagine you're looking through the side of it there, and this is that's the front. Now, in the back of the tube you have an electron gun, which I'll just call gun. Okay, I'm simplifying this. And from the gun, it generates a stream of electrons, negatively charged electrons, which actually fire. If you didn't do anything with the beam, it would fire out straight to the screen at the front, and you would end up with a dot just there. Now the electrons, when they hit the front of the tube, there's actually a phosphor coating on there, and it illuminates light. So in effect, it's converting the electron flow, or the electron beam, to light, and that's what you see is the green dot that you saw earlier on the screen. That's exactly what's happening. But obviously we can move the dot. We can move it up, down, left and right. So in order to do that, you need to be able to deflect the beam somehow inside of the tube. There's different ways of deflecting beams. You can do it using magnetic fields, using a coil, a deflector coil, and that's the way they used to do it in old TVs. They used to have a deflector coils in there which would actually wrap around the tube, and then you could deflect the beam to produce a TV picture. But in an oscilloscope they do it the other way, which is using electrostatic deflection. And electrostatic deflection just use plates. So inside you actually have 4 plates, but I'll only draw 2 right now for the purposes of the diagram. And those 2 plates, you can apply voltages, positive or negative, to those 2 plates. So like I said, if you didn't have any difference in the voltage across the plates, the deflector plates, the beam would just go straight through, okay, and hit the front in a dead straight line. But if you apply, say, a positive voltage to one of the plates and a negative voltage to the other plate, because the electrons are negatively charged, they will be attracted to the positive plate. Do you remember in the earlier video we explained that electrons actually move from negative to positive in terms of actual particle movement in physics? Well, that's what's going to happen here. So you can actually go straight through here, and this would actually pull the beam up like that, and now the dot is there. So it's been attracted to the positive plate, while at the same time it's been repelled from the negative plate. Okay, so by changing the voltage, if you swap them around, then the beam would go down. So by changing the difference of voltage from these 2 plates, these are the Y plates, you can move the dot up and down, which is what we just did earlier with the 9-volt battery. It's exactly what we're doing. You're not putting 9 volts across the plates, you're actually putting a few hundred volts across the plates. There's an amplifier inside of the scope which amplifies the input to the voltage that's needed for the plates, but it's calibrated. The X plates are basically exactly the same, but the other way. So the X plates then move the dot from left to right, which is your time base, or your X deflection. Now on the screen now we've got what we call a sine wave, an equal amount of movement from positive, and then it slowly stops and it goes negative, and then it stops at the bottom and goes positive again. It's all quite smooth. There's no squareness or peaks or anything. It just kind of smoothly goes up and down. And what we're seeing here is an actual sine wave. I've got a signal generator plugged into the input at the moment, producing that sine wave. And there's 2 things that the scope can tell us immediately. It can tell us the amplitude in volts. How big is that signal from the trough to the peak, or if you like, the negative point to the positive point. The difference, the height, is the amplitude or the voltage, peak to peak voltage. And we determine that using the attenuator control, which tells us how many volts does it take to go from one division to the next. So each division, or each, if you like, it's actually a square centimeter box, is determined by the voltage coming in through the attenuator. At the moment it's set to 1 volt, so it takes 1 volt to get from one box to the next. And in this case you can adjust the position of the of the sine wave, just up and down. And I hope you can see it sits on this bottom line here, and it goes all the way up to this top line here. So if you count the boxes between, or the graticule divisions between, it's 1, 2, 3, 4, 5. That's 5 centimeters or 5 graticule squares. You can see that this is set to 1 for each one. That's 5 high from peak to trough, so it's just 1 times 5. So this sine wave is actually a 5 volt signal, a 5 volt peak to peak signal. That's not RMS or anything, that's peak to peak, just determined by the attenuator control. So straight away it's working like an AC voltmeter. We can actually see the voltage amplitude very clearly in the actual peak amplitude. Okay, now the other thing the scope is actually telling us is the frequency, or the time duration it's taking to go from one part of the cycle to the next. You know how big one cycle is by looking to see where the waveform repeats itself. So if you look at the waveform here, it's going up, goes the top, coming down. Now you might say, well, is that not the same? Is that not one waveform because it's repeated at the same voltage point? And the answer is no, because that one was going up and this one's going down, so they're different. So keep going, then you hit this part, well that's a different voltage, so that's definitely not the end of the cycle. Now what about this one? Yeah, it crosses through the 0 and it's going positive again. So what you can say is that those points are the same. That is one entire cycle. It goes up, down and up, and then it starts to repeat the next one. So you can discard all of that and just use this part here. Now again, like what we did with the amplitude and the voltage measurement, you can measure time using the time-based control. And the time-based control, in this case, it's set to 2 microseconds per division. That's pretty quick. It's much faster than we had it before for the speech pattern. So this one is 2 microseconds. It takes for the dot to go from there to there, there to there, there to there. It's all 2 microseconds. So if you look at the waveform, how many graticule squares are we dealing with here? It's 1, 2, 3, 4, 5. So that's 5 multiplied by the 2 microseconds, which means you don't really need a calculator for that one. That's 10 microseconds. 2 times 5. So 10 microseconds of time it's taking to go from the beginning to the end of a single repeating waveform. This would be another 10 microseconds, but we're not interested in that for the time measurement. So the scope's told us 2 things straight away. It's told us the amplitude of the signal, how big it is in terms of voltage, and it's also told us the time period it's taking for a complete waveform, where the waveform starts to repeat itself. That's one full cycle. These are cycles. What if you want to know what frequency that is? We know what the time is, but what's that in terms of hertz or kilohertz or even megahertz? What frequency is it? Well, you could just take the probe and plug it into a frequency counter and it would tell you straight away. It would tell you what the frequency is. But what if you don't want to do that? You want to use the scope to do it. Maybe you don't have a frequency counter already. So let's work it out. So we had 5 times 2 micro7 graticule positions on the screen, which equals 10. So it's 10 microseconds of time for a complete cycle. For a whole cycle, 10 microseconds of time takes to get from that point to that point. And you can rewrite 10 microseconds as 0.00001 of a second. They are the same. It's easier to say 10 microseconds, of course, but you can enter it as 0.00001 of a second. Now, to determine frequency from time, it's very simple. It's just frequency equals, and it's 1 over time, or the reciprocal of time. So frequency in hertz would be 1 over 10 microseconds. It's our time. Okay, so we can do that. We'll plug it into the calculator. So it's just 0.00001, and on a lot of scientific calculators you have a 1 over k reciprocal, so that's 1 over that, which gives you 100 kilohertz. That's 100 to the 3, so it's 100 kilohertz in other words. So we've actually figured out what the frequency, and I've written it down here already, 100 kilohertz or 100,000 hertz, same thing. And that is actually the frequency of the sine wave that we've measured earlier. Now we can check that because my signal generator actually has a frequency display on it, conveniently. Let's just have a look at that. Where are we? And I hope you can see that's actually reading 100 kilohertz. It's got the little kilohertz LED illuminated here. 100 kilohertz. So that's the signal that we're putting in to the scope, sine wave. And indeed, after the measurement, that's exactly what we calculated from the screen. Okay, another thing worth talking about is on oscilloscopes is Z modulation. You're familiar with the X position and the Y scale, and I always remember X as being across because X is across, so I always remember it that way. If you're not familiar with graphs and axes, then that's a simple way to remember it. X is across. It's that way. So, and Y is up and down. Think of it that way. So what's Z modulation? Well, you've got X and you've got Y. So what on earth Z? Can't come out the front of the screen. We haven't got 3D or anything. So what's Z? Well, all Z is the intensity of the dot, the intensity of the beam. And it's just, I can simulate it by turning the brightness down. That's Z modulation right there. So you can turn it down and you can make it brighter again. What you normally have is a connector on the back of the scope, like a 4mm banana socket or something like that, or a BNC, and you can modulate the beam using Z modulation, and that can have some very useful applications when you get more advanced with using oscilloscopes. Z modulation can actually come in useful for displaying certain things. And one thing worth noting about with oscilloscopes is the triggering, and that's why this is what allows this trace to be almost looking stationary. It's not flying all over the place. It's synchronized. The dot is actually synchronized, so we can see a continuous wave locked on the screen, as if it almost like it was a storage scope, except it's not a storage scope because if we disconnect it, it goes away. There's our signal. Put the signal back on. There it is. But it looks almost like a storage scope. It's not flying to the left or flying to the right. It's quite locked. So what's allowing the beam to synchronize to the input signal? What's allowing the time-based control to be exactly correct with, you know, the actual input, high and low and high and low? Well, that's down to the triggering, and you have a trigger control on all oscilloscopes. And all that's really doing is sensing when the input level is above a certain point or below a certain point. You can have a positive trigger or a negative trigger, and it's looking for a certain point where the voltage gets to, say, for argument's sake, let's just say it gets to 1 volt. And when it gets to 1 volt, it starts the trace. Off it goes. And then when that's gone off the screen, it waits until the signal gets to that trigger point again, and then so on repetitively. So every time we see a trace, it's being locked by the trigger. And I can show that if I turn the trigger off. And you can see, actually the beam's gone completely. I'm triggering at different positions within the waveform. That's why it looks like it's moving left to right. We're actually picking a different point to trigger from. I'm turning it up, I'm turning it down. So it's actually, it looks like it's moving the the actual waveform. If I turn the trigger off, there. Now can you see it's just like a big, I'll turn the brightness up a little bit. It's just like a big bar. And that's all those sine waves being displayed, but they're not being synchronized anymore, so it's just a complete mess. And every so often you might see some almost synchronized sort of patterns like that. You can see some weird sort of like patterns and quite complicated signals, and of course that's not representing the true waveform at all. That's not showing us a sine wave. We don't actually know what the waveform really looks like. We've got some nice interesting patterns to look at, but it's not really giving us any information at all. It's not triggered. Put the trigger back on, and there it is, completely locked solid. So triggering is vital if you want to show a stable image, so then you can actually determine what it is that you're looking at, and then you can do your time and you can do your amplitude measurements. So triggering is important, and you can get positive or negative triggering. This button here allows us to flip the trigger, and you'll notice the waveform now starts to go negative then positive. go to positive triggering, goes that way. Now it's looking for a positive trigger level. Now it's looking for a negative trigger level. It's going negative. It's going positive. So you can have negative, positive, and in a lot of cases you've got some sort of filtering as well, like HF filtering, high frequency in other words, so it only allows high frequencies to trigger. Or you can have LF, which is low frequency triggering. It only allows low frequencies to activate the trigger circuit. So that's triggering, and that's keeping the image completely locked. So then you can take your measurements and you can see clearly what the shape of the waveform is. Another aspect of oscilloscopes worth mentioning is the bandwidth capability of the Y amp, or of the input of the oscilloscope. So as you can see, the signal's coming in right now through the BNC input here, and it's our 100 kilohertz signal, sine wave, and we already know the frequency from the time divisions, and also from the amplitude from the vertical axis, the Y axis here. So we've already done all that, but this is all well and good at this frequency at 100 kilohertz. It's well within the oscilloscope's capability. But what happens if we start to actually wind up the input frequency higher than 100 kilohertz? What if we take it to a few megahertz, 5 megahertz, 10 megahertz, and so on? Well, with oscilloscopes of this age, and this scope's probably about 20 years old, I think, thereabouts, there is a limitation to the bandwidth of the input amplifier circuitry within the scope itself. And as you go higher in frequency, you will start to see an attenuation of the amplitude. In other words, the calibration is not correct anymore. And my signal generator at the moment only goes up to about 2 megahertz, so I can't really wind it up any higher to show you that, but I'll simulate it just by turning the amplitude down, just so you can see what it would look like, that's all. As the frequency goes up, let's say it's up to like 1 megahertz, then 2 megahertz, then 3 megahertz, then 4 megahertz, and then it goes below the trigger level and you can't see the signal anymore. And I'll just turn it back up again to where it was roughly. So I think you get the idea that as the frequency goes up to the input socket, there is a point where it will start to, where the display will start to attenuate, where it will reduce in amplitude. So I think it's about a 10 megahertz scope. No, 20 actually, just in the front. It says 20 megahertz here. So it'll handle up to 20 megahertz, which is quite high. Much higher than I was just demonstrating there. Some really old scopes only go up to about 5 megahertz. So you've got to be careful of the input frequency that's actually going into the input socket. I have another scope above here. This is my Gould storage scope, and this scope will go up to 200 megahertz. So actually you can go to a much higher input frequency into the input socket on this, up to 200 megahertz. This is a Gould DSO 475. It's quite an old model, made in the late 80s. Again, picked up cheap on eBay, and it came to me broken, so we fixed it, and it's turned out to be a very nice piece of equipment at the end of the day. The main advantage of this scope, as I say, is the input frequency bandwidth is very high. It's 200 megahertz, it's pretty good. But it is a storage scope, and as you can see, there's nothing plugged into the input yet. We appear to have a display here. This is something that was caught in the memory from, I don't know, weeks ago when I was doing something. And it's a snapshot of the actual waveform. So even though you've got the input disconnected, you can freeze the display and look at it at any time. The other advantage with scopes like this, and modern scopes are like this as well, all of the new ones that you can buy now, they have built-in mathematics functions which calculates the peak-to-peak voltages, the RMS voltages, and also the time period and the frequency. So the time and frequency calculation that we did earlier is actually done internally here and displayed on the screen right for you in real time as well. So as you would vary the input signal to this, it would be constantly recalculating what the values are, so you don't have to keep getting your calculator out all the time, which is extremely handy, especially things like frequency readout. And all modern scopes, like I say, they all have this built in now. It's pretty much a standard feature with any scope. any digital scope on the market now, and also PC interface boxes that you can plug into your computer and have it on your computer screen. The maths functions are already built in. So we're looking at a waveform on the screen here, and it's flickering a little bit, but never mind. I'll turn up the time base. It should reduce the flicker a little bit. It's because it's reacting with the shutter speed of the camera. It doesn't actually look that flickery if you look at it directly on the screen. It's just reacting with the camera. But I hope you can still see. We'll have a high voltage here, a positive voltage, then a very quick drop, and then a low voltage at the bottom. It's actually 0. So because we've got this very steep, sharp angle going on, and I'll just reduce the time base so you can see more of the cycle, more of the waveform. You can see it's a square wave, basically. You've got a high, and you've got a low, and it goes high again, with very sharp fall and rise edges. Okay, so that's a square wave. So we can again determine what the amplitude is, and we can also determine what the time period of whatever it is that we're looking at, and we can figure out what the frequency is from that as well, using 1 over time. So again, let's have a look at the let's do the amplitude first. So you can see that it's actually at 1, 2, 3 and a half graticule units or divisions from the low point to the high point. So that's 1, 2, 3 and a half. So it's 3.5 multiplied by the attenuator for voltage input. And at the moment it's 1 volt per division. 1 volt per division, so it's very simple. 1 times 3.5. The amplitude is 3.5 volts. So straight away that's actually telling us the voltage of the waveform, peak to peak, from the most negative part to the most positive part. So that's 3.5 volts. Now what about the frequency or the time period anyway? Okay, well again we look at the time-based control, and at the moment it's set to, don't know if you can see that or not, 20 milliseconds per division. 20 milliseconds. So it's 20 milliseconds for every division. Now remember where we said before, you want a complete cycle. You don't want half a cycle or 2 cycles, you just want 1 complete cycle. And the cycle from start to end is where it starts to repeat again. Well, this is the high point here, and it's triggering on the signal going from 0 to high. So that's the start of the signal. It's always at the beginning. Follow it down. That goes to the bottom. So that's not a cycle. What about this part? A low to a high? Yes. Low to a high there, and low to a high there. So that is 1 complete repeating signal. Low to high, low to high. That's a high to low, so that's in the middle of the cycle. So we need to count how many divisions, just like we did before. 1, 2, 3, 4, 5, 6. 6.5. It's in the middle of a graticule there. So it's 1, 2, 3, 4, 5, 6.5. So it's 6.5 multiplied by the 20 milliseconds. Okay, you can probably do it in your head, but let's get the calculator. Let's have a look. Okay, so 6.5 times 0.02, which is the 20 milliseconds, and that's 130 milliseconds. Okay, 130 milliseconds. So that's our time period, 130 milliseconds for a totally repeating waveform. Okay, from the start to the end. And remember, to work out the frequency of that, it's just 1 over time. So just press the reciprocal button, and what we're getting there is 7.69 hertz. Let's say 7.7 equals 7.7 hertz. 7.7 hertz, and that's the frequency. And yes, you've guessed it, you've probably already seen it. That is our little 555 oscillator, astable multivibrator that we made in the very first video with a little blinky flash LED. So that's actually flicking on and off at 7.7 hertz, okay, which is also 130 milliseconds. And I seem to remember what I said. I was guessing at the time period, and I think I remember saying something like about 100 milliseconds. And I wasn't far off. It was just a guess as well, without measuring it. So yeah, it was pretty close. Slightly slower than I thought it was. Just a little bit. 130 as opposed to I thought it was 100 milliseconds. And like I say, that turns out that's 7.7 Hertz. Okay, and that's pretty much it for this basic introduction to oscilloscopes video. I hope you found it useful. Like I say, these can now be picked up on places like eBay really cheaply, under £100, second hand obviously. You know, you can get a second hand storage scope for about the same sort of money if you're prepared to actually work on it and fix it. Probably a little bit more for a working one. And you can get interfaces that plug into your PC, an interface box where it's all done in the computer and it gives you a nice digital display. You can also get LCD versions or OLED display versions now from various manufacturers, and they do all the inbuilt mathematics to calculate, you know, RMS, peak to peak, and time interval and frequency all in the box. So these ones are old, but they give you a good idea how the modern ones actually work, an appreciation for the old CRT technology as well. And there are plenty of them around. Sometimes when you're doing fault finding, it's actually an advantage to use an analog scope. You don't always want a digital scope. Sometimes, because everything's been digitally sampled through an ADC sampler inside of the scope, you do get artifacts at certain frequencies. You can have problems at certain frequencies, and you've got to be aware of that when you're doing measurements and when you're testing things. It's not a case of what you see is what you get, not always. Whereas with an analog scope, you know, there's no sampling frequencies going on, and what you see really is truly the voltage coming in. As long as you're within the bandwidth of the actual scope itself, then it will look accurate. So I use both personally. I have digital scopes on the PC. I use this CRT storage scope here, which is a Gould. It's called a 475 model, and also a good old analog Hameg on the bottom there, which you can pick up, like I say, really quite cheap, and they're very, very useful to have on the bench. I use mine almost daily for repairing audio circuits like amplifiers, digital circuits for looking at data bus activity and looking at clock frequencies of oscillators and all kinds of things. Really, really very useful pieces of equipment. So if you haven't already got one, I would encourage you to get one and have a play. Doesn't cost that much for a second-hand one. Okay, well, I hope you've enjoyed the video. Thanks again. See you next time.